Hello, I'm your teacher, Mr. Davenport, and this lesson is a short lesson that deals with lever problems. I entitled it Lever Problems Made Simple because my purpose in this lesson is to make this as simple as possible. I'm going to introduce you to some concepts that really apply not just to levers but to all simple machines, and that's my purpose in this lesson. In this lesson, we're only going to talk about one kind of lever. We're going to talk about a first-class lever. And in doing so, you're going to understand and learn about some concepts that apply to all types of simple machines. Uh, Levers, first class, second class, and third class. Concepts also apply to pulleys and block and tackles. It also applies to things like inclined planes or gears for that matter. So all of the concepts that you learn here are going to carry through to future lessons. So pay real close attention. I'm going to make this as simple as I possibly can. I think you'll understand it by the time I'm done. Well, a lever is a simple machine. It's a simple machine like this first class lever. And this first class lever is so simple, it only is made of basically two parts. The triangle that you see here is what's called a fulcrum. The top of that triangle is a pivot point, and sitting on that pivot point is this beam. Simple machines do work in one motion. You notice I didn't qualify that by saying that levers do work in one motion. All simple machines, no matter what they are, do work in one motion. That's what identifies a machine as a simple machine. It can do work in one motion. Sure, you push down on one side of this beam with a force, and you can lift a weight on the other side. So if you put a mass on one side, you can lift it upwards by pushing down with a force on the other side. And this is a first-class lever. Why is it a first-class lever? Well, I'll talk more about this in a later video, but this is a first-class lever because the fulcrum is in between the force you apply to it over here and the force that you're lifting over here, the mass that you're lifting. So that's what makes it a first-class lever as opposed to a second-class or a third-class lever. But like I said, we'll spend some time talking about three kinds of levers in a future video. Simple machines do work in one motion. All simple machines have two sides. Here's our first-class lever. Look at this. We have an input side. That's a side where I'm going to put a force into this machine. It also has an output side, a side where the force comes out of the machine. On the input side, you put work in, a force in. On the output side, you get work out, a force out. So those are the two sides of any simple machine. And again, any simple machine, not just a lever, not just a first-class lever. Could be an inclined plane, a block and tackle, a pulley, any type of simple machine that you can think of. They all have two sides. That's it. An input side and an output side. A side where you put a force in, a side where you get a force out. A side where you put work in, the input side, and a side where you get work out, the output side. All simple machines produce what's referred to as a mechanical advantage. Of course they do. You want to use a machine to make work easier to do. Mechanical advantage tells you literally how much a machine is going to help you. The mechanical advantage tells you how much the machine will multiply any force that you put into it. Here's our first-class lever again. I know by looking at this lever that this lever will multiply any force that I put into it by a factor of 1 and only 1. What does that mean? That means that whatever force I put in on one side, that's the only force I can lift on the other side. How do I know that the mechanical advantage here is 1? Well, the input side is 2 meters long. And guess what? The output side is also 2 meters long. And it's because the two sides, the input side and the output side, are the same length, the same distance from the fulcrum. That's what tells me that the mechanical advantage of this machine is 1, and that it will multiply any force I put into it by a factor of just 1. So, does this mean that the machine doesn't make work easier to do? Well, of course not. Whether or not a machine makes work easier to do or not depends on what you want the machine to do. In this case, this machine, as it's designed, enables you to change the direction of the force that you put into it. Rather than increase the force, it allows you to change the direction of the force. So if you want to design a machine to make work easier by allowing you to change the direction of a force, this is the machine. A good example would be the pulley at the top of a flagpole. If you put 10 newtons into pulling the rope down, you can lift the same force as a flag on the other side, but the flag goes up the pole while the force that you're pulling on the rope with goes down. The pulley at the top simply changes the direction of that force. So it does just exactly what it's designed to do. Well, let's take this to the next step. What happens if we change the length of the input side with respect to the output side? Well, here's what happens. Here's our first class lever again. The input side here is 2 meters long. The output side, measured from the fulcrum to where the weight is that you're going to be lifting, is 1 meter. The two sides are different lengths. The input side here, 2 meters. Output side, 1 meter. If I apply a force of 100 newtons to the input side of this lever, then I might ask, how much force can I get out on the output side? And I can figure that out by figuring out the mechanical advantage. And specifically what I'm going to do here is I'm going to figure out something called the ideal mechanical advantage. Why is it ideal mechanical advantage and not just mechanical advantage? Well, the ideal mechanical advantage, or IMA, ideal mechanical advantage, means that we're not taking into account the friction involved in this machine. It is a perfect machine, which really doesn't exist. It's an ideal machine with no friction. So I can calculate the mechanical advantage, the ideal mechanical advantage for this machine. I do it like this. I compare the two sides of the machine. We have an input side here, and we have an output side. The ideal mechanical advantage is simply the ratio between the input side and the output side. The ideal mechanical advantage then is the input side, 2 meters, divided by the output side, 1 meter. And what this means is that when I find the answer is ideal mechanical advantage is equal to 2. This lever will multiply any force that I put into it on the input side by a factor of 2, because its ideal mechanical advantage is 2. The ratio between the input side and the output side is 2. By the way, the input side is also referred to as the effort side, and the output side is referred to as the resistance side. So I'm moving a resistance force with an effort force. I put an effort force in, I can move a resistance force, and in this case you can see here that the resistance force I can move is 200 newtons. The input force, the effort force, is multiplied by this machine by a factor of 2, which allows me in this case to lift 2 times as much as I put into it. That's a good introduction to how this works. So let's go ahead now and work on a few very simple lever problems to get used to using this idea of ideal mechanical advantage. All right, let's go ahead and solve a problem. And problem one here is obviously a first-class lever, just like we've been looking at. And the first thing to do here when you look at a lever is to identify the input side and the output side. Well, the input side is where you put a force or work into the machine. So over here where we have a force of effort of 200 newtons, that's going to be the input side, and I'll label that with an I. And over here where we have an object that's being lifted, then I'm going to label that O for output. So we have an input side and an output side. And the first step here is to go ahead and figure out what the ideal mechanical advantage of this machine is. Ideal mechanical advantage, if you recall, is equal to the input side divided by the output side. And when we plug some numbers in here, here's what we get. The input side is 4 meters long. The output side is 1.5 meters long. So when we solve this problem, we get, on my little calculator, I get an ideal mechanical advantage of 2.7. Meter, of course, cancels out. This is a ratio between the input and output sides. And so what we're saying here is that whatever force we put into this machine is going to be multiplied by a factor of 2.7, and that would give us the weight that we can lift on the other side. The question here is, what is the resistance force that we can lift with a 200 Newton input force? If we put a force of effort of 200 newtons in, how much resistance can we move on the other side of this lever? Well, we can figure that out like this. We can say that the force of resistance is equal to the ideal mechanical advantage multiplied times the force of effort. In other words, the resistance that we can lift is the ideal mechanical advantage times the effort. Remember what ideal mechanical advantage is. It tells us how much our force of effort is multiplied to give you a particular force of resistance. It allows you to predict what you can lift with this simple machine. So we solved this. The ideal mechanical advantage, remember, was 2.7, and we're going to multiply that by the force of effort, the force we're putting into the machine on the input side, and that force is 200 newtons. So our force of resistance that we can lift is 2.7 times 200, and that gives me 540 newtons. So there's our answer. The answer here is 540 newtons right there. Problem solved. Well, let's go ahead and work on another problem. And problem 2 is a little bit different. In problem 2, we're going to be finding the effort force rather than the resistance force. So in problem 2, we're going to start with the ideal mechanical advantage. That's going to be our starting point. So let's go ahead and do that. Ideal mechanical advantage is equal to the input side divided by the output side. And we can plug some numbers in here. Ideal mechanical advantage is equal to the input side, which is 4.6 meters, divided by the output side, and that's 2.2 meters. And if I solve this for the ideal mechanical advantage, I wind up with, it looks like 2.1. I'm going to round it to 2.1. And again, meters factor out, so it's just a ratio. There's no unit of measurement here. Now, what can we do with this ideal mechanical advantage? Remember that the ideal mechanical advantage multiplies your effort force to allow you to predict what resistance force you can lift. Like this, ideal mechanical advantage is used to find the resistance force. Force of resistance is equal to the IMA times the force of effort. But in this case, we're trying to find the force of effort. So we're going to have to rearrange this to solve for force of effort. In order to do that, I'm going to divide the IMA out of each side, just like that. So the new relationship here is force of effort is equal to the force of resistance divided by the IMA. And you know, that just stands to reason. That's just logical. Think about it. The ideal mechanical advantage for any machine will multiply your effort force to tell you what resistance force you can lift. And so therefore it must divide the resistance force. So we can plug some numbers in here. The force of effort is equal to our resistance force, 150 newtons, divided by the ideal mechanical advantage, which is 2.1. And when I solve this, our force of effort works out to 71.4. It rounds to 71.4, and that's going to be newtons. And there's our answer, 71.4 newtons. All right, problem 3. Well, problem 3 is very similar to problem 2. In this case, we're going to be figuring out what the effort force is, not the resistance force. But we're going to have the same starting point. We're going to find the ideal mechanical advantage. And of course, the ideal mechanical advantage is the input divided by the output sides. And if we plug some numbers in here, the input side is 6 meters long. The output side is only 1 meter long. And when we solve this, we wind up with an ideal mechanical advantage of 6. Now, we're finding the effort force. Recall what we said in problem 2. We said that the ideal mechanical advantage multiplies the effort to tell you what the resistance is, or it divides the resistance to tell you what the effort is. So we're going to divide the resistance force by the ideal mechanical advantage. So it's going to be force of resistance divided by the ideal mechanical advantage, and that's going to tell us what our force of effort is. How much input force do we have to put into this to actually be able to lift this 840 newtons? So we can solve that. It's easy. All we have to do is divide 840 newtons by the ideal mechanical advantage, which is 6. And that looks like it gives us 140 newtons. And that's pretty good. We can lift 840 newtons with a 140 newton input or effort force. Problem solved. Okay, let's go ahead and give this one more try with one more simple problem, and then we'll review a little bit. Problem 4 says we have a force of effort of 100 newtons, and we're going to figure out how much resistance we can move with that effort, that input force of 100 newtons. And again, the beginning point is to calculate the ideal mechanical advantage. And the ideal mechanical advantage is equal to, remember, the input side, that's the length of the input side, over the length of the output side. Well, when we figure that out, we have the input side is 2 meters, and the output side is going to be 1 meter. And so our ideal mechanical advantage for this particular first class lever is simply going to be 2. In other words, whatever force we put into it, the machine is going to multiply that by 2. So we can figure out what the resistance force is. Remember that the ideal mechanical advantage multiplies the effort force to help you predict what the resistance force is going to be. So the resistance force is simply the ideal mechanical advantage times the effort force. And if we plug some numbers in here, the ideal mechanical advantage is 2, and the effort force, remember, was 100 newtons. And so the force of resistance that we can lift with this particular first class lever is going to be 200 newtons. Now we stop and think about this. We're talking about forces here. We're not talking about work. Remember that work is a force times a distance. And one very important concept that we learned in the past is that work and energy are equivalent. And if you look at the law of conservation of energy, you can't get any more energy or work out of a machine than you put into it. So even though we can move a resistance force of 200 newtons, it moves up only half as far as we push this side down, and that keeps the work the same on both sides. So we can just throw this out. If we push down on this effort side and we push this side down a distance of, I'll just say 5 centimeters, then this side is only going to move up half of that, or 2.5 centimeters. Why? Because remember, work is force times distance, and we can't get out of the machine any more work than we put in. It has to be the same. It's the conservation of energy. Well, let's go ahead and end this lesson with a little bit of review. Remember, a lever is a simple machine, and simple machines do work in just one motion. A good example of a simple machine here was our first class lever. It's simple in construction. It only has 2 parts, the fulcrum and the beam, and it does work in one motion. Remember also, all simple machines have only 2 sides, an input side and an output side. And remember, I said all simple machines. Wouldn't have to be a lever. It could be any simple machine. They all have only 2 sides, an input side and an output side. A side where you put work or force into the machine, and a side where you get work and force out of the machine. Remember, all simple machines have a mechanical advantage. They produce a mechanical advantage that tells you how much the machine will help you, how much it will multiply any force that you put into it. Also keep in mind that the work that you put into a machine and the work that come out have to always be the same. Okay, also remember that the lever we looked at here had both arms the same length, and that gave it an ideal mechanical advantage of 1. So this one didn't increase any force you put into it. This one simply changed the direction of the force, which is one of the things that any simple machine can do. A machine can be designed to do nothing more than change the direction of a force. Ideal mechanical advantage doesn't take into account the friction that machines produce. It's for an ideal machine, a machine that doesn't have any friction. But it's useful in being able to predict the effort force or resistance force, the force that you have to put in to move an object, or how much force you can lift by putting a certain amount of force in. In this case, if you looked at this problem, we had a machine, a first class lever, that had an ideal mechanical advantage of 2. It multiplied the effort force, 100 newtons, by 2, and told us that we could expect to be able to lift about 200 newtons with this particular lever. Remember also that ideal mechanical advantage, or IMA, is the ratio between the input and the output sides of any simple machine. It multiplies the input or effort force to allow you to predict the output or resistance force, or it does just the opposite. It divides the output or resistance force to tell you what the effort force is. And that's what you should have learned in this lesson.